Well, thank you very much, everyone, for attending this evening's talk. The talk is organized by the Institute of Mathematics and its Applications, the London branch, for which Professor Stephen Lynch is on council. He also sits on a number of other committees, including the EDI committee, for which I am chair. I'm also on council at the IMA. My name's Dr. Howard Horton, and you can Google, so I'm not going to waste my time on that. But Professor Lynch has a wonderful, very interesting talk. I'm not going to waste much time talking about that. I'm just going to ask him to get into the meat of the talk. I'm going to ask you to come a bit closer, if you could, from the back. Okay, thank you very much for your indulgence. You can ask questions, but perhaps at the end of the talk. It's going to be quite an exciting talk, and you're going to last for that time.
Yeah, we talk about 50 minutes, 45, 50 minutes.
Okay, so the talk's going to be between 45 and 50 minutes, and please get your questions ready because it will be a very exciting talk, and we have a limited amount of time in it. Okay, thank you very much, Stephen.
Okay, thank you, Howard. Okay, so thank you everyone for coming. I realise it's a Friday evening and you probably think you've got better things to do, but I guarantee you will enjoy this talk. So I was at MMU for many years, and I think I joined there in about 91. We were Department of Maths and Physics. Shortly afterwards, they closed the physics department. And I think it was towards the end of the 1990s that the numbers of maths was going down to about 20. So I thought, I've got to do something here. So I started a schools liaison. And after about 25 years, I visited over 100 schools in the Greater Manchester area. And now we had hundreds of students on the course. And this talk really helped. So it's a mathematics talk, but you'll notice as I go through this, there's no mathematical equations in this. Okay. So the talk is called Brain-Inspired Computing. So we have a schematic of a brain here. This is our invention. So this will be my epitaph. I'll have this put on the gravestone or on a piece of wood or something when I die. So this is called a binary oscillator half adder, and it's the basic component of how all computers work. Okay, so I'm going to explain to you how neurons work in the brain. Well, we're going to be we're going to take transistors out of conventional computers and phones and all your mobile devices, and we're going to replace them with something else. And they're called threshold oscillators. Already, we have 5 potential avenues of research. So how many of you have heard of a memristor? A few. Okay, so we can build oscillators with memristors. How many of you have heard of Josephson junctions? Okay. Oh, that's more. Okay, so we can also build threshold oscillators with Josephson junctions. Obviously, biological neurons. Here are biological neurons. Little animation here. You'll see there's little white lights here going up and down. These are called axons. I'll explain what those are in a moment. We can also build oscillators from transistors. I was at a conference yesterday with semiconductor experts, and I asked quite a few of them, what's the minimum number of transistors required to build a threshold oscillator? And nobody knew the answer. Okay, so I'll talk a bit more about that in a moment. And then about 15 years ago, a research group at Southampton were able to build all optical threshold oscillators. And again, they're simulating how the brain works using optical fibers. So the objectives, from this very simple idea in mathematics, we think we can build the world's fastest supercomputer. And this is a photograph of the current world's fastest supercomputer. It consists of thousands of trillions of transistors. In order to run this supercomputer, we have to use nuclear power stations. And that's not the only problem. These things get very, very hot. So countries all over the world are diverting rivers. So in here, you can see these large pipes. They're diverting rivers, pumping water through these pipes in order to keep these in order to keep these supercomputers cool. Okay, so they're not very environmentally friendly at all. So we've come up with something that can replace this. All around the world now, you'll see it on the news. Countries are spending billions and billions of dollars making more and more nuclear power stations to power not only supercomputers but data centers. You'll have all heard of the explosion with AI. So the world is just accelerating ahead and building more and more nuclear power stations, to power all of this. As well as building the world's fastest supercomputer, there's another application in biology. So this is not computers now. We're going to build what we call assays for neuronal degradation. So we're going to use biological neurons to build simple logic and memory circuits. And I'll explain why we would want to do that in a moment. Okay, so we've got Hinkley Point C nuclear power station is currently being built now. Somerset, England. It's going to cost, well, it's going to cost more than £35 billion. They've said it will be operational between 2029 and 2031. But you know what engineering is like, it'll probably be 2035 before it's actually running. It will generate 3,200 megawatts of power. And this is the energy required to power transistor-based supercomputer that can emulate one human brain. Okay, so your human brain now, a typical human brain is consuming about 20 watts of power. Yeah, 20 watts of power. IBM have estimated that in order to perform the tasks of one human brain, you'd need an even bigger computer than this to emulate the task of one human brain, and you would need a nuclear power station with thousands of megawatts of power. Okay, so that's giving us a massive hint that transistor computing is not the best way to compute. Okay, so we're going to use, that's what we call it, brain-inspired computing, you know, because obviously nature, over millions of years, creatures have developed with these threshold oscillators. Why? It's because it's the most economical way to compute. If our invention works, instead of using a nuclear power station to run a supercomputer, we would be able to run our supercomputer on a laptop, and you could literally connect your laptop to some solar panels. Okay, so these solar panels generate about 50 to 70 watts of power. So one solar panel generates about 250 to 400 watts of power. So we can easily, you know, run our laptops just using solar panels. Recently, we've set up a company. It's called OSSI.tech. So it stands for Oscillator Supercomputer Chip Innovative Technologies. The reason I was in London yesterday, I went to a conference with a group of people who work with semiconductors. And so we've now got to the stage where we need to start building prototypes, because we've done all the theory, everything works perfectly, but now we want to start building prototypes. Okay, and this is a really interesting story. So back in 2001, this is John Borison. He was an undergraduate student of mine in 2001. He came to my office one day and he says, "Oh, I've heard about this Schwarz circuit. It's a nonlinear electrical circuit. I've heard about this circuit, and I want to do my final year project, you know, do the mathematics." Well, he actually wanted to physically build this Schwarz circuit. I had to say to him, "Oh, sorry, John, the physics department closed 2 years ago, so all of the, you know, all the resistors and everything have gone now." But so I do mathematical modeling. So I said, well, what we could do instead is we could look for hysteresis in Schwarz circuit, because nobody had ever found it before. And within 1 month, John was able to find hysteresis in Schwarz circuit. So we wrote a paper together quite quickly. We submitted it to the International Journal of Bifurcation and Chaos, and the editor of that journal is Leon Schwarz. Okay, Leon Schwarz is known as the grandfather of nonlinear electrical circuits, and we'll come back to Leon in a bit. Okay, but this is a fantastic, inspirational story for undergraduates. In fact, it's so inspirational that while I was at MMU, I inspired other members of staff to do a similar thing. And by the time I left MMU, we had 5 journal papers published over a wide range of topics. So for open days and visit days, it's great. You know, you can show the students we had these 5 journal papers published by undergrads, so we could say to them, in 3 years' time, this could be you, you know, publishing your own results. So this is what we call a nonlinear electrical circuit. So we've got an inductor, 2 capacitors, and a resistor, and there's a nonlinear component. So once we have, you know, once you build these components, physics and maths and electrical circuits are closely aligned to mathematics. So once we have these electrical circuits, we can write down differential equations in order to simulate you know, how these behave. Okay, so I know you've all heard of artificial intelligence by now. So artificial intelligence is where we get conventional computers, obviously transistor-based computers nowadays, and we want to get them to act like the human brain. You know, so in the future, we'll have driverless cars. We'll be using this a lot in medicine. And you know, the applications are unbound. You know, large language models, AI is going to be everywhere. So this is using computers to act like the human brain, okay? And that's gonna dominate all of our lives for many, many years to come. Our invention is the opposite. So with our invention, we take how the biological brain works, and we're going to build a new type of conventional computer. Okay, but in this conventional computer, there won't be transistors. There'll be something else. And as I say, this laptop would be equivalent to a transistor-based supercomputer, which would, you need the size of a building to run that. So this is using biological brain dynamics to create, and it's a conventional computer. Okay, so I've given this talk many times in schools, and all the kids straight away say to me, "Oh, is this quantum computing?" This is not the same as quantum computing. This is different to quantum computing. This is a conventional computer. So everything you can do with your transistor-based computer, you can also do with this computer. Okay, so what are these neurons? So biologists can take like a mouse or a rat or whatever. They kill the mouse or rat, freeze its brain, and then you take slices through the mouse brain. We can look at these slices under a scanning electron microscope. We get images like this. And then from computer science, we can use image processing techniques. So this is image processing techniques. We can look for the edges of these neurons. So here we've colored the neurons again with image processing techniques. We can give colors to individual neurons. So you can just about see the cell bodies here. So these are all cell bodies. And then these things going out are axons. And these axons can be really short. So the axons can connect neurons to neurons within the brain, or they can be meters, it can be a meter in length because they can go from the brain down to your legs. So these axons can be long or very short. So these are just, some pictures of neurons. There was a research group in Harvard who were trying to map, trying to figure out, well, how would we figure out how all of the neurons are interconnected in one human brain? And just to give you an idea of how complex the human brain is, using current technology, it would take 4 million years just to hear how every individual neuron is connected to every other individual neuron in one human brain. So the human brain has about 100 billion neurons. Yeah. And one neuron can connect about 1,000 other neurons. Yeah, they're very, very highly interconnected. Okay, so what are these oscillators? So the oscillation you're probably most familiar with is your heart. You probably might have heard your own heart. You can feel your pulse. So if you go to the hospital, get yourself connected to a heart monitor, you do bum, 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 bum. So these are oscillations. So your heart beats about once a second. Yeah. We have lots of oscillations in the human body. Another famous one is the circadian oscillations. So this is your wake-sleep cycle. So in the morning, you have neurotransmitters. So there's lots of chemistry in this. So in the morning, you have chemicals that wake you up, and all the excitatory neurons are going mad, and you wake up. And then in the evening, you get tired, and then your inhibitory neurotransmitters kick in. So there's lots of chemistry that happens right through the day. It affects your mood, and it affects everything in your brain. And you have this 24-hour cycle. You wake up nice and bright, you get tired, and in the evening, you get tired, you go to sleep. So there's that 24-hour cycle. But these are not the only oscillators. So the neurons, so this is a schematic of a neuron. So you've got the cell body and a cell nucleus, and then you have these axons. So these are also oscillators. But these oscillate 1,000 times in 1 second. So in your brains now, your brains are, the neurons are oscillating 1,000 times a second. So, if you try and imagine what 1,000 beats in 1 second sounds like, you can't really get your head around it. And then I've written papers about angiogenesis, which is new blood vessels forming, from pre-existing vessels. So, when you're fetus, this is really good because this is how human bodies are created. But obviously, later on in life, you can have these things growing from vessels, and then they feed growths, and this is cancer. Okay, and you can have oscillations in cancer growth. These are not the only oscillators. For example, retinal cells in our eyes oscillate, muscle cells oscillate. So our bodies are just full of these oscillatory processes, all on a wide range of time scales. So if you ask a lot of people what is an oscillator, they won't be familiar with what an oscillator is, and they won't realize that our bodies are just full of these oscillators. Okay, if you remember right at the beginning, I showed you a video with these little lights moving up and down the axons. So we have these kinesins, which are motor proteins that move towards the positive end of a microtubule, and then dyneins, which are motor proteins that move towards the negative end of a microtubule. And they've actually proven that this happens. So I'm going to play a little video now. So these things transmit, they can transport organelles, vesicles, and proteins within an axon. So here's the axon, and these microtubules are within the axon. Okay, and this is what actually physically happens. Okay, so these kinesins and dyneins actually walk up and down these microtubules. So you can see there's mechanical engineering there, which kind of blows your mind. It's on really, really small scale. And you can imagine, trying to do the mathematical modeling for this is quite complex. And so you have this bi-directional cargo transport just within the axons. And as well as that, we've got voltages and currents and lots of other stuff going on at the same time. Okay, so where does the maths come into this? So in 1950s, Hodgkin and Huxley at the time were working at University of Plymouth, and they were looking at these giant squid axons. Okay, so the giant squid axons in a giant squid, they're about 1 meter in length. And what they were trying to do is they were trying to figure out how does the voltage and current flow down these axons. So in the 1950s, they worked on this biological material. At the end of the experiment, they throw them up to the ceiling, and you can still go to Plymouth now, and they hang like stalactites from the ceiling where they worked. And in order to simulate what actually happened, they built simple nonlinear electrical circuits. So here's the nonlinear electrical circuits again. So you can see we've got capacitors, we've got resistors, and in this case we've got 2 nonlinear resistors. Okay, and from this work, they were able to simulate how current and voltage are generated in this giant squid axon. Fantastic work. And in the 1960s, they were actually awarded a Nobel Prize. Okay, they were awarded a Nobel Prize because they figured out how the voltage and current flow down these axons. Unfortunately, their work was incorrect. Okay, it was mainly correct, but it wasn't quite correct. I'll explain why in a second. Okay, so in the average human brain, we've got 80% excitatory neurons. So the way I explain this to school kids is we've got these excitatory neurons which are oscillating, they're connected to other neurons, and an excitatory neuron would switch another neuron on. So when you wake up in the morning, you can imagine all these neurons are switching other neurons on. So we have excitation. We also have 20% of the neurons in your brain are inhibitory. So an inhibitory neuron will switch other neurons off. Yes, so we have excitation and we have inhibition. Yeah, so those are the 2 main things going on in the brain. So in the morning, you have lots of excitation, and in the evening, when you're trying to get to sleep and you're trying to shut your brain down, that's when your inhibitory neurons kick in. This is called the postsynaptic neuron. You can see I've given them colors here. Obviously, in your brain, you don't have green and red and blue neurons. Yeah? They're all just skin color. So what we do is we put, well, you can put a little extra current into these neurons to get them towards threshold. So again, when I'm explaining this to kids, you've got your neuron, we pump current into the neuron, and we reach a threshold where it kind of starts to spike, and then the more current, it oscillates, and then more current, it gets faster and faster and faster, and then it goes off. So that's typically what happens with a biological neuron. You can see that, you can make videos of this. So you got your neuron, you pump current in, it starts to kind of flicker a bit, and then it slowly oscillates, it gets faster and faster and faster, and it goes off. So we call that a threshold oscillator. And you can see here, if we excite this excitatory neuron, then what happens? We have excitatory neurotransmitters going to the postsynaptic neuron, and it raises the voltage in the postsynaptic neuron. So you can see there's lots of chemistry in this. Yeah. So that raises the voltage there. If we excite the inhibitory neuron, then that one fires, and it actually lowers the potential in the postsynaptic neuron. Okay, so we're either moving it towards excitation or moving it away from excitation. Okay, a brief history of computing. So in 1948, the world's first program was run on Manchester University's small-scale experimental machine, and they called it the Baby. Has anyone been to the Museum of Science and Industry in Manchester? Okay, yeah. Did I take you? Oh, you told me. I didn't take you. Okay, but when you walk through the main door, the Museum of Science and Industry, you turn to the right and you'll see a full working replica of the world's first programmable computer. So computer enthusiasts got together in 1998. They built a full working replica. And you can still go and see it being used now. Your calculators, the calculators that you have in school or whatever, they are more powerful than this computer. One of the principal components of this was a vacuum tube oscillator. Now, the vacuum tubes are about this big. They came in smaller and smaller sizes, but you can imagine they use a lot of power. Yeah, they glow, and you need a lot of power to power these. Then in the 1940s, 1950s, really, the transistor was invented. So we have these three arms. We have a collector, we have an emitter, and then in between we have a base. Now, these are also kind of threshold devices, because if there's enough current goes into the base, then it kind of switches this on. So if there's a base current which reaches a threshold, then that enables current to flow through the transistor. And you can think of this as a switch. So when people talk about transistors, the easiest way to think about it is a switch. So if this is on, then current will go through the transistor. Yeah, so this is how transistors work. Now the question is, and I've just shown you, transistors, came along in the 1940s and 50s and quite large, but over the decades, they've got smaller and smaller and smaller and smaller. And now you can literally fit 50 billion transistors onto a postage-size stamp. Yeah, they are really, really small. But I'm sure you've all have heard that we're reaching the limits now, because these transistors are getting so small that we're starting to get quantum interference, because they're so small, we've got quantum effects. So the world needs, something else, because the transistors are reaching the limit. I say that, but at the conference yesterday, it was clear that the world is still quite happy to pump billions and billions and billions into the transistor, and build all these nuclear power stations, etc. Okay, so the question is, well, we've gone this progression from vacuum tube oscillators, which used a lot of power. Transistors get less power, but you can see from what I've shown you before, they still consume vast amounts of power. So what's next? So by the end of this talk, you will know the answer to the what's next. What's the future of computing like? Okay, I show this to so I teach first year programming at Loughborough. They're all doing a computer science degree, and on the whole degree, they're never shown how a computer works, which I find bizarre. Yeah, and it'll be the same in every computer science department probably in the world. They're doing a degree in computer science, but they're never shown how does a computer work from the very basics. So this is obviously transistor-based computing. When we used to have physics departments, there is a physics department still here, is it? Imperial?
Yeah,
yeah, okay, great. Okay, so you have breadboards. So this is called a breadboard. You can put all of these things together. Do they still use breadboards during the physics department? I would think they do. So here are the transistors. You can see these are quite large, but it's great to show students this. And students have great fun. In fact, the conference I was at yesterday, as part of EDI, they every year they offer, I think it's like scholarships to 500 females, because they try to get more females into electrical engineering, and they give them the BBC Micro, and and Raspberry Pi and things, and they get them building simple circuits, etc. So here we have two transistors in series. So this is how we depict transistors. Here's the base. So you can, if you remember, if this current goes into the base, then it switches this transistor on. If current goes in this one, then it switches the transistor on. So most computer scientists around the world, they're shown the logic gates. So they do the truth tables. If you've got 0 and 0, you get 0. 0 and 1 gives you a 0. 1 and a 0 gives you 0, and 1 gives you 1. Well, what does that physically actually look like? And it's easy to see with this series circuit. So when you put transistors in series, the only way current will flow all the way through is if this one's on and this one's on. Both of them have to be on in order for current to flow through. And then when you show this to computer scientists, they get it straight away. If you think of it as like these switches, they understand, rather than just looking at this obscure thing. Okay, so now we've got an exclusive OR gate. And you can see for the exclusive OR gate now, this is getting a bit more complicated. We've got AND gates and OR gates, and we've got a new symbol here, which represents an exclusive OR gate. And you can see for an exclusive OR gate, we need 5 transistors. Okay, so what does an exclusive OR gate do? When an exclusive OR gate, you'll see the light bulb will only come on if either A or B are on. If both of them are off, the light bulb stays off. And if both of them are on, the light bulb stays off. Okay, so you have to wire the circuitry in order to get this logic. Okay, so does anybody know why we need an AND gate and an exclusive OR gate? No. So no. So I asked this to. In fact, I even asked this to the final year students, 200 of them. You know, why do you need an AND gate and an exclusive OR gate? And nobody knew the answer on a computer science degree, which I think is shocking. Yeah. Well, you're kind of there, but it's not the answer. There is a clear answer. Yeah. So the clear answer is we can build a half adder. How many of you have heard of a half adder?
Yeah.
Yeah. So a half adder is the basic logic component of any computer. It's the most basic logic you can do. So what's the most basic logic you can do? You can just add 2 bits together. Yeah. So, you know, think back to primary school, you got 0 plus 0. So, you know, if you think of your 10, you know, units and tens that you do in primary school. So 0 plus 0 is no units and no tens. 0 plus 1 is 1 unit and no tens. 1 plus 0 is 1 unit and no tens. And 1 plus 1 is no units and a 10. So now we're doing binary, yeah, because, you know, computers work in binary. So so in binary, 2 is 1 0. Yeah, so that's how this, and you can see the circuitry for this. You can see how, you know, quite complicated this is. Yeah, and if you count, we actually need 8 transistors for a half adder. Yeah, and, you know, lots of wiring here, lots of resistors. So that gives us a basic half adder, just adding 2 bits together. Okay, so computers work in binary. So the very earliest computers, you know, we had light bulbs. So you could read the computer by looking at the light bulbs. So here we've got, you know, this is like your units, your tens, your hundreds, and your thousands. So if you've got light bulb on, light bulb off, light bulb off, light bulb on, then that equivalent to binary, that's like 1 0 0 1. Yeah, so that's, and then if you look at the denary, that's, you know, this is like, this thousands is like an 8, hundreds is a 4, tens is a 2, and units is a 1. So 1 0 0 1 in binary is equivalent to 9. Now with threshold oscillators, you know, you can think of it like the bulbs. If an oscillator is oscillating, we think of that as R1. Yeah, and if it's not oscillating, that's your 0. So that's where the binary comes in. It's either oscillating or not oscillating. So it's like light bulb on, light bulb off. Okay, so this is our invention. It's called a binary oscillator half adder. So back in 2008, so I should have said, John did his undergrad with me. Because he got a journal paper, he got an MSc at Bristol. He passed his MSc at Bristol. Then he went on to do a PhD at Exeter with Peter Ashwin. And he was looking at coupled oscillators with Peter Ashwin. Then he got a postdoc at University of Manchester. He's working with Steve Ferber. Anyone heard of Steve Ferber? Yeah, he's like ARM chip. Yeah, you can look it up later. Spinnaker project. He's world famous. I think he's just about retired now. And then after all of that, John came back and started working with me. And then we came up with this crazy idea. Okay, and I'm going to explain to you how this works in a second. So you see, it's a very simple design. It's much simpler than the half adder using transistors. So here we have 2 inputs. You know, so these will be like your 1s and 0s, etc. And we have 2 threshold oscillators. Okay, there's a number of ways to do this, but the easiest way to do this is oscillator 1 has got a low threshold. So oscillator 1, you don't put much current in and it starts to oscillate. Yeah. Oscillator 2, we set at a higher threshold. So you need more current for that one. Yeah. So for oscillator 2, you need more current before it starts to oscillate. Yeah. So we've got a low threshold oscillator and a higher threshold oscillator. Back in 2008, we went to the university and we said, we've got this crazy idea and we think we can drastically reduce the number of components needed to build computers. But we said we need to speak to somebody in industry. So it took 2 years. Yep, 2 years, and then we saw Professor John Bancroft at STFC in Dursbury, and we explained our idea to him. And within 20 minutes, he said, "Oh my God, you've got to patent this idea straight away." Okay, so it took us 2 years to get anybody to listen to us in university. In industry, 20 minutes. Yeah, that's the kind of it's crazy. Right. So then we went back to the university and we said, a professor in industry has told us we've got to patent this idea straight away. And it took another 2 years for us to get the patent. So we originally went to the patent lawyers with 4 sides of A4. You know, John and I used to do journal papers. So we wrote it like a journal paper. We said, here's our idea. So they had a quick look at it. I said, sorry, lad, you've got to explain it in far more detail. And you can see that the patent is actually 57 pages long. Okay, and I'm going to explain it to you now in 2 minutes how this works. But when you do the patent, You've got to cover all the bases. So it was 57 pages when it was actually. So you can see that was published in 2012. Okay, so how does it actually work then? Okay, so using transistors, you can see you've got the AND gate and you've got the exclusive OR gate. And remember, this consisted of 8 transistors. Yeah, there's 8 transistors for the half adder. Again, we've got the truth table. You look down the column, 0 plus 0 is no units, no tens. 0 plus 1 is 1 unit, no tens. 1 plus 0 is 1 unit, no tens. And 1 plus 1 gives you 1 10 and no unit. Yeah, that's how it works with transistors. So the question is, well, how do we do this with threshold oscillators? So using threshold oscillators, if you remember, when the oscillator is oscillating, that's your 1. So the inputs are also oscillations. Yeah. So if you look down the first column, there's nothing going into A, nothing going into B, nothing goes into O1, nothing goes into O2. So, no current goes in, they stay off. So 0 plus 0 is no units and no tens. Okay, now let's say that either A or B are on. Yeah, so either A or B are oscillating. So what happens is, because it's either, we have sufficient current goes into O1. Yeah, so there's only a bit of current. Yeah, so we have enough current goes into O1, that one oscillates. Yeah, so O1 comes on. But when you look at O2, because only either A or B are on, there's not enough current. Yeah, O2, we've got the same amount, but it stays off because I had a higher threshold. Yeah, so that's the easy bit. So if you look down the columns, we've got 0 plus 1 is 1 unit and no tens, and 1 plus 0 is 1 unit and no tens. Yeah, everyone with me so far? Okay, now the next bit is the bit that nobody else in the world had thought about. How do we know that? Because we applied for the patent and we got it. Yeah, and when you see how simple this is, you'll believe it. Okay, so how do you do 1 plus 1? Okay, so now let's say A and B are on. Okay, so if A and B are on, then we've got loads of current goes into O1, so that threshold is definitely reached, so O1 switches on. And now because both of these are on, yeah, we've got more current going in. So now the threshold of oscillator 2 is also high enough, so that one switches on. So we've got O2 is on, O1 is on, but we have this inhibitory connection from O2 to O1, so immediately oscillator 2 switches off oscillator 1, the inhibition. So O2 immediately inhibits O1. Yep. So if you look down the last column, we've got 1 plus 1 is no units and a 10. So 1 plus 1 is 2. Yep. Is that going to change the world? You think, oh, when I show school kids this, like, so what? 1 plus 1 is 2. That's crazy. Okay. Okay. Rather strangely with this, if you remember, 80% of the neurons in your brain are excitatory and 20% are inhibitory. And that's exactly the ratio for this simplest of logic components. Spooky? Well, we don't know yet. Okay, so that's how that works. Now, this is where it starts to get interesting. So as I said, with transistors, you can see, the world's largest computer fills a building. And you think, well, why do you need it? If you can fit 50 billion transistors onto a postage-sized stamp, why do you need a building you have to do the computation? And the simple reason is, if you double the processing power, if we double the processing power using transistors, we at least double the number of components. Okay, so with transistor-based technology, we have an exponential increase in the number of components. Yeah. Exponential. Now, I'm sure you all have done A-level maths. You've got y equals e to the x, exponential growth. Okay, it turns out if we use threshold oscillators, we can double the processing power with a linear increase in components. Now, this is why John and I want to speak to people in industry. We saw this and we thought we could build computers with instead of using thousands of trillions of transistors, we can, thousands of trillions exponentially only equates to a few thousand with the linear. Yeah, and I'll show you what that means physically in a minute. Okay, so here's our schematic of the half adder. 1 plus 0, 0 plus 1, etc. The next most complicated circuit, I should have told you, the next most complex circuit is where we add 3 bits together. If you think about logic, add 2 bits. What's the next most complicated thing you can do? Just 3 bits. So this is the full adder. So we're doing 1 plus 1 plus 1. And it turns out that for a full adder, you still only need 2 threshold oscillators. Okay, you can see you've got more inputs now because you've got 3 inputs. So this is called a full adder. But you can see you still only need 2 components. So we can double the processing power with a linear increase in components. Okay, which means far fewer components. So that's what John and I saw. The professor at Dursbury, as soon as he saw this, he went, oh my God, you've solved the power problem. And that's why he said you've got to patent this idea straight away. Okay, now as well as performing logic, we've got half adders, full adders. You can go on and you can easily look this up on the internet. How do you connect all of them to do more and more complex logic? And you can just build all of those up. Circuits get more and more complicated. As well as performing the logic, if you want a conventional computer, you've also got to store memory. Yep. So the way transistors store memory is they use something called a set reset flip-flop. So in this little black box here, there are a certain number of transistors. And the way to think about set reset flip-flop is if this, so we've got two bulbs. If one is on, the other one's off. And if you cause a switch, if this one comes off, that one goes, if this one comes on, it switches that one off. Okay, so it's like a switch. Okay, it's called a set reset flip-flop. But in order to cause a switch with transistors, we have to charge the line. So the way to think about it is if you want this light bulb to come on, you have to push this button. You have to keep hold of it. You have to keep hold of it because you need, it's a bit like a well, with a marble. You've got to give it quite a big kick to get the marble out. Yeah. So you need to give this quite a big kick. So you have to charge the whole line. And that's why when you've got your laptops on your lap, they get very warm. Yeah, they get warm because of this line charging. Now, the circuitry to build a set reset flip-flop with threshold oscillators, you can see it looks very similar, but we have this one's trying to switch that one off, and this one's trying to switch. They're mutually trying to switch each other off. Yeah? And it turns out that we can cause a switch with these threshold oscillators. We can actually cause a switch with a single pulse. Yeah? And a single pulse means very, very little energy. Yeah, just a little, and it switches. Yeah, that's far less energy than having to charge the whole line. And this is just one component. You can imagine with these memory devices, you have whole matrices with billions of these things. So you can imagine this power being multiplied by billions. So again, you can save massively on power. Okay, I'm now going to come back to Leon Schwarz. If you remember, here's John Borison. Yeah, here's Steve Ferber, who's the Spinnaker project guy. I think he's retired now. Leon Schwarz, I think he's still active, and he must be about 86 now. Yeah, so he's still going strong. Right, if I'd have asked you at the beginning, who's heard of Leon Schwarz? Nobody would have heard of him. His daughter wrote a book. Has anybody heard of Tiger Mother? Yeah. Okay, so his daughter wrote a book called Tiger Mother, and it's about being brought up in America under strict, Chinese rule. Yeah. So his daughter is more famous than him, and yet this guy, honestly, he's a professor at Berkeley, University of Berkeley in California. So, but as I say, his daughter's more famous than him. Anyway, so in the 1970s, he was looking at this picture. So I'm sure you've all heard of a resistor. A resistor relates voltage and current. If you see this on an oscilloscope, you usually get a straight line graph. Yeah. A capacitor relates voltage and charge. Yeah. And an inductor relates current and flux. So for many decades, electrical engineers have been building all your devices with resistors, capacitors, and inductors. And if you think back to Hodgkin and Huxley, they were simulating how neurons work using capacitors, resistors, inductors. Unfortunately, their results were not quite right. There was a mistake in their work, and there was something missing. And what was missing was this memristor component. So this is a really good story in mathematics. So in 1971, Leon Schwarz was looking at this simple picture. Now, again, there's lots of examples like this in history. You think, well, why hasn't anybody else noticed this picture? Because resistors, inductors, capacitors have been around for a long time. Why didn't anybody else notice that there should be something relating charge and flux? So Leon Schwarz noticed this, and he used mathematics to prove the existence of a fourth fundamental component. Yeah, that was in 1971. And he's known as the grandfather of electronics, and he's at University of Berkeley. Right? So, so people were looking, well, what is this memristor? It wasn't until 37 years later, 37 years later, HP Labs actually built a memristor. Okay, so that gives you a clue as to why what we're suggesting hasn't come to fruition yet. Okay, with these things, it can take decades and decades before something tangible appears. Okay, so it's called a titanium dioxide memristor. If you connect this to an oscilloscope, you'll see it acts a bit like a resistor, but you have this hysteresis. It's actually called pinched hysteresis. So it acts like a resistor, but it's got memory, and hence the name is called a memristor. It's like a resistor, but with memory. Yeah, and now there are research groups all over the world working with these memristor devices. When HP Labs first made this device, they said they were going to revolutionize computing and there were going to be completely different types of computers, but that hasn't quite come to fruition yet. Okay, nobody yet has made something new with these memristors. It's the same with graphene. So, I worked in Manchester for a long time. Graphene was invented and everyone was saying, oh, it's going to change the world. Everything's going to be made of graphene, but there hasn't been really anything remarkable that's changed the world yet. So these inventions keep coming out and we're going to change the world, but nothing happens. Okay, so with memristors, so this was a research group in China. And what they did is they built simple threshold oscillators using memristors. Okay, so these are two threshold oscillators. There's oscillator 1, oscillator 2. And you can see, if you look down the columns, 0 plus 0 is no units, no tens. 0 plus 1 is 1 unit, no tens. 1 plus 0 is 1 unit, no tens. And 1 plus 1 in binary is 10. So they built our half adder using memristors. And then they extended this to show that you can build a full adder. And so with a full adder, we've got, if you look at the last column, we've got 1 plus 1 plus 1. And 1 plus 1 plus 1 in binary is 11. So you can see it works. So that works perfectly as well. I've currently got an undergraduate doing a project with me, and we're currently building a memristive set reset flip flop. So we should I think we've got the results, so we'll probably publish that this year. Okay, so what I've shown you so far, transistors, memristors, it's all room temperature, and there's nothing really that's going to change the world there. But this now is where it gets really, really exciting. So in 1962, Brian David Josephson predicted something called the Josephson effect. Okay, so this is what we call, it's called a superconductor. It's a Josephson junction. These things can be built 1,000 times smaller than biological neurons. Okay, if you cool them down to 4 Kelvin, they become superconductors, which means that you don't really need any voltage. Current just flows. These are extremely, extremely, extremely low power devices. I was saying the brain uses 20 watts of power. These use thousands and thousands, probably even millions of times less power than biological neurons. But this is the shocking thing. Look at that. They oscillate. They oscillate 100 million times faster than biological neurons. Now, it's difficult enough to think about a neuron oscillating 1,000 times a second. How can you possibly imagine something going 100 million times faster than 1,000 times a second? Okay, but these things actually exist. In fact, we went down to, many years ago, we went to Rutherford Appleton, and we were talking to researchers there, and showed them the idea. They had the cheek to say to our face that, oh, yesterday we had some people from Cambridge, and they were really clever. They said that to our face. We couldn't believe it. And then they said, these Josephson junctions, they're just theory. They don't physically exist. It's all just theory. So John and I were a bit annoyed. So we went back and we found out it's not just theory. Okay, so the research group at Colgate University in New York. So we're now working with Ken Segal. And what they did in 2010, so this was 2 years after our invention, they built simple circuits here. So these big X's here are Josephson junctions. This part of the circuit acts exactly like a biological neuron. This part of the circuit acts exactly like a chemical synapse. And electronically, so here you've got a neuron. If this bias current here is positive, this neuron switches another neuron here on. So we've got excitation. So all you need electronically is for the bias current to be positive. So we can do this very, very easily electronically. With transistors, memristors, Josephson junctions, this is really easy to do electronically. To get inhibition, all you need to do is this bias current has to be negative. As long as this bias current is negative, this neuron switches another neuron off. So we can perform excitation and inhibition really, really easily with electrical circuits. So that paper was published in 2010. When John and I first saw this, we thought, oh, bloody hell, somebody's beaten us to it. But they're doing something else. They're not building computers. So this is Ken. He came to see us, how many years ago was it? It was longer than that. So this is us playing table tennis in the garden. This just to show school kids that, you know, we're not mad inventors with our white lab coats on, and, you know, we're just normal people. We played table tennis. I think we drew 4-all. It's a classic game of table tennis. So here we have the excitatory neuron is blue, switches the green one on. And here we have the inhibitory neuron blue, switches the green one off. But remember, this is all happening in picoseconds. Yeah, this is, you know, really, really fast picoseconds. Again, this is not just theory. So Ken works with actual physical Josephson junctions, and he's had some publications in 2017 and 2019. He's now working as part of a company. He's done like us, so he set up his own company, and they're going to make physical artificial intelligence machines using these Josephson junctions, and the synapses connecting the branches, the different layers together, are going to be optical fibers where they use single photons. Yes, they just use single photons, you know, extremely low power, and there's nothing faster than the speed of light. Yeah, so they're going to use Josephson junction neurons with optical fibers with single photons, you know, doing messaging between the layers. Okay, now, so with maths, so my big thing is I'm written books on maths packages like Python and MATLAB and Maple and Mathematica. So this is really nice to show students. So on the left, we've got a Ficciu-Nagumo limit cycle. So this is the, you know, this your limits. There's no limit cycle, no oscillation, and you pump more current in, and then you get the oscillation faster and faster, it goes off again. But we can show this with mathematics. This is called a phase portrait, and this is related to my PhD, which is very pure mathematics. So here you can see that this is called a limit cycle. So the limit cycle, you know, represents an oscillation. So my PhD was about, well, how many limit cycles can systems have? Yeah, so that's a very pure maths. I know AI is kind of solving all the problems. The problem I was working with is very pure maths. It's over 100 years old, and nobody's anywhere near solving that problem. The next big news item to come through AI will be when it solves one of the millennium problems. Okay, so there are lots of maths problems which have been around for, you know, decades. The human race is nowhere near solving any of them. As soon as AI cracks one of them, then I think we're in trouble. Yeah, because that's more or less saying that AI is cleverer than anyone in the human race. Yeah, so it could happen within 5 years, 10 years, 50 years, but it will happen. It's going to happen. The next one is it's a Morris-Lacar model. And what's different with this one, instead of just going from neuron off to neuron on, what we have here is we have what's called a small amplitude limit cycle. So we've got a neuron, you know, oscillating, and then we pump current in, and then all of a sudden, bang, there's a higher oscillation. Okay. Now it turns out with nonlinear systems, you can build these things so they can have multiple different amplitudes. Yeah. So we haven't done this yet, but instead of just having a 0 and a 1, you know, like in normal computers, you can imagine with highly nonlinear systems, you can have states naught. Well, you know, the different amplitudes, you can have like a 1, a 2, a 3, a 4, a 5. So you can have lots of different states, which you know, multiplies massively your computational abilities. It's a bit like, you know, quantum computing can have lots and lots of different states. Well, these you could have lots of different states as well. There's going to be physical restrictions, but that's again something that we haven't looked at yet. Okay, if you remember, I told you Ken is doing actual physical modeling with these Josephson junctions. So in this cylinder, this was an interesting story. So in 2011, John and I went to New York, and we knew Ken was there. So we went to meet Ken. There's a company in New York called Hypris, which actually manufacture Josephson junction circuits, mainly used by the military. And when we went into the building, there were all these massive pipes, you know, running in the ceilings. And we thought, oh, that's how they do the supercooling. You know, that's how they get everything down to 4 Kelvin. These massive pipes must be really complex. But those massive pipes were for the printing, you know, just printing the circuits. In a corner of a room, and you can see here, there was well, they call this a rack. And on the rack, there's like a cylinder. And in this cylinder, well, he's simulating here a cortical column. So you've got, you know, thousands of Josephson junctions, which act like a cortical column. And this thing is plugged into the wall. It's just plugged into the wall. So you don't need like nuclear power stations or anything to do this. Okay, and so this is operating at 4 Kelvin. As I say, there are thousands of Josephson junctions here. What Ken is doing for his research is he's simulating how a brain develops, the cortical column of a human brain. He's simulating how that develops over decades. And because these things oscillate 100 million times faster than biological neurons, physically here, this equates to minutes. Yeah, so you can run experiments to see how the neurons connect and develop in minutes, and biologically, that's equivalent to decades. Yeah, so that was the focus of their research. Okay, last summer, we were working with one of Ken's second-year undergraduate students. So Ken, just for a second-year undergraduate project student, just said to the students, can you build a set reset flip-flop with Josephson junctions? Because, and I'll explain why we do Josephson junction set reset flip-flops rather than the logic. And within a few weeks, he did it. Yeah, he did it. He built a set reset flip-flop with Josephson junctions. And it turns out, rather spookily, that the more stable system is when you go from a small amplitude limit cycle to a large amplitude limit cycle. That is more stable than on-off. And we don't know why yet. We haven't got our heads around that yet. Also, when we build the physical model, and we know when we start building prototypes and things, so in Ken's machine, they've got software, and they say if they can simulate it with the software, then they can definitely build it. So when they simulated the set reset flip-flop, it turns out that they had to connect the set reset flip-flop with a resistor. And again, we don't know why yet. Okay, but when you physically build these, with mathematics, you don't need another component. Everything works perfectly. But when you physically do it, you need to incorporate something else. And in this case, you have to put a resistor between the two to keep them stable. We don't know why yet. Okay, but you can see that it works perfectly. And there are actually 3 stable states. Remember that there's an off, there's a small amplitude, and there's a large amplitude. So that gives you 3 states. So again, if you multiply it up, and again, we don't know, how many possible stable states could there be? If you had 10, then again, that multiplies massively the memory capabilities of these devices. So there's still lots of work to do. If you remember, I told a while back that we can double the processing power with a linear increase in components. That's equivalent to this chip here. Okay, so when we went to Hyperus, they loved our idea, and they said we can use their picture. So this is a photograph of the world's fastest arithmetic logic unit chip built with Josephson junctions, and on here there are 8,000 Josephson junctions. And it's lovely. When you zoom in, it looks like a city. It's a really nice circuitry. And so that's a linear increase in components. The equivalent with transistors, you remember transistors, an exponential increase in components. You need thousands of trillions of transistors. So these two are equivalent in computer power. So we can replace this with one chip in a laptop, and that would be more powerful than this. Because 8,000, linear it's much bigger than thousands of trillions. Okay, now this is where it gets scary, right? So remember I said that these chips work at 4 Kelvin. Anybody know how cold space is? 3 Kelvin. Isn't that weird? 3 Kelvin. Yeah. So we could build a computer this size in space. Yeah. Josephson junctions are also radiation hard, so you wouldn't even have to shield the computers. You can use solar panels to power the supercomputer. Now imagine, so the way I explain this to school kids, imagine our brains have got 100 billion neurons. Ants have got millions of neurons. Now when we look down at an ant, the ants with their millions of neurons, they know what they're doing. They're doing all kinds of complicated stuff. And when this computer looks down on the planet Earth, this huge brain will look down, and we will just look like ants. We'll be running all over the surface of the planet the Earth. We all know what we're doing, but you think, what could that computer do? So what you can imagine is a computer the size of a building, well, a brain the size of a building, yeah, with each component is 1,000 times smaller than a biological neuron, and each one is oscillating 100 million times faster than biological neurons. And that's like science fiction, and you think, what could that do? Yeah, so that chip would be more powerful than that. Okay, now that's not the only application. Okay, you remember all this came from a very, very simple idea in mathematics. Okay, so this is another avenue of research. So I'm now working with researchers, chemists and biologists at Loughborough. So this is not building computers now. This is applications in medicine. So the human body can suffer from over 500 neurological conditions. I'm sure you've all heard of Alzheimer's, autism, Parkinson's, epilepsy, stroke, brain damage, several, and there's over 500 neurological conditions. Right? So I'm now working with Eric Hill. Eric Hill is what we call a stem cell researcher. I'm sure you saw it on the news recently. They can now take skin cells and grow an embryo. Anyone see that? I think it was about a month ago on the news. So Eric can take skin cells and he can grow excitatory neurons and he can grow inhibitory neurons. Okay, we don't have to kill any animals. We don't have to take neurons from human beings. We can just grow neurons to suit whatever we want. Paul Roach is the chemist, and he kind of builds the platforms, to connect all of these neurons together. So we wrote a paper in 2020, just doing a mathematical modeling of how we would do this, but now we're physically getting around to it. So this lower picture here shows biological individual neurons. So these little white lights here, they are biological neurons, and you can see that these like lines, they are the axons connecting the neurons together. So we've got this multi-electrode array. So these are called electrodes. So what we can do is we can pass electricity down the electrodes, switch the neurons on, and we can also read from the electrodes, and we take the electrodes back to the computer. And you can actually see some of the neurons are firing on this array. Okay, this isn't science fiction. This is what's happening in labs all over the world. Yeah, so we can actually read, what these neurons are doing. There's a research group at Harvard who've genetically modified a worm. You can shine light on certain neurons. You can make it turn left. You can make it turn right. You can make it think it's hungry. This worm has only 300 neurons. Now, this gets really interesting because what you think, when we start building our circuits, and you're building half adders, full adders, and you get more and more complex. And when you think about early life forms, you think, well, how many neurons do you need before a creature becomes self-conscious? Because you think, well, this thing is alive, it reproduces, it eats. Has it got any intelligence? Does it know it exists? And then you start thinking, how complicated does the circuitry have to be before it becomes self-conscious? There's another branch of science called optogenetics. So you can you can use fluorescent dyes. When you shine a light on an excitatory neuron, it will glow green when it's firing. And when you shine a light on an inhibitory neuron, it will glow red when it's firing. So we're going to build our little logic and memory circuits using biological neurons. Not only can we see the input and the output, but we can actually monitor what the circuit is doing in between. All the neurons going on and off. So Eric Hill can, he can take Parkinson's disease neurons, epilepsy disease neurons. So you can actually grow the neurons with the disease already in, and then we can build our little circuits. You can imagine we've got 100 of these circuits, and then we drop drugs on them. Drug A, drug B, drug C, and we see which circuits will function for the longest time. Because currently the world doesn't have that. If you take neurons and just put them on the dish, you don't know what the function of those neurons are. But we're going to make the world's worst calculator, 0 + 1 + 1, and we know the output. And then we can start storing memory. Yeah, we store simple memory on these devices, and then again we can tell when the memory starts to fade. Yeah. Okay, this is hot off the press. I think this is about 2 or 3 months old now. So they're now working with these things called organoids. So this little lump here is just like a little lump of brain. And the reason we're working with organoids is because these are extremely stable. So we can keep these alive for a long time. You can just about see here the axon. So there's lots of axons go from this organoid, which is, big cluster of neurons. And what we're going to do is we're going to excite this. We're going to shine light on this organoid. And the reason we prefer to shine light is neurons don't like electricity. They don't like to be outside a biomass and putting electricity. So we can just shine light on them. They're in a biomass. They're quite happy. And you can just about see that the neurons are glowing. And as I say, in the future, we can use dyes. So this will glow green. And you can just about see it's exciting some of the neurons over here. Okay, so we've done the excitation. All we need next is inhibition. So what we need is this one to be firing, and then this organoid switches that one off. Yeah, so we'll have our, and then we can build half atoms, and this should be a Nature paper. Because if you think about it, you know, we're going to build simple logic and memory, conventional computing circuits out of biological neurons. No, nobody's ever done that before. Yeah, so that before I die, I want a Nature paper, and I think I'm pretty sure that will be one way that we can get that. If you're interested in my research, I'm on ResearchGate, so you can download all of my papers for free. This thing here, you can now buy cuddly neurons on Amazon. I think they're about £8. I took them home to the kids, you know, thinking that they're pretty ugly little things. And both of them, I think I gave one to Talia, and Seb said, "Oh, I want one as well." So kids even love these cuddly neurons. So as I say, we've set up a company called OSSI. We're now working with TechWorks, so we're really nice people with TechWorks. So these are like semiconductors. So as I say, everything is concentrated on the semiconductors. But we spoke to a guy from IMEC who works with semiconductors, and they've already done some work with Josephson Junction. So I'm going to be speaking to him over the coming weeks. I've written lots of books, and you can see that I've incorporated my invention onto the front of the books. I run work. So one of the reasons Loughborough University employed me is I teach Python to all of the undergraduates and postgraduates and alumni and staff across the university. So this book covers biology, chemistry, data science, engineering, economics. I'm going to do sports science, physics. And you can see one of the strengths of this book is the interdisciplinary science. Okay, the only way we came up with this idea is through interdisciplinary science. If we didn't know the biology and the chemistry, there's no way we could have come up with the idea. So it shows the strength of interdisciplinary science. Okay, and then as you can see, what time is it now? It's a good time. Okay, so we'll just open it up to questions then. Yeah.
Just a quick question. If I understand correct, your inhibitors kind of act like the minus operation in the computer, right?
Yeah.
So other than the four basic one operations like and or not, you introduce another one called minus, and that can.
Well, it's like a not. Yeah, it's kind of a not gate, isn't it? Yeah. Yeah.
Okay. So my question is like, could you go back to the full adder?
The full adder. Full adder. That one full adder, yeah, that's a full adder.
So I do not quite understand what happened if all of the three gates are open.
Yeah, that's a good one. Yeah. Okay. So what happens is, if all of these are on, yeah, then you have loads and loads of current goes into that one. That one starts to oscillate, right? Now, loads of current also goes into this one. This one tries to switch that one off, but there's too much current goes into that one. It stays on.
So it's because like.
Honestly, it's so easy to set up. It's literally solving mathematical inequalities. So you have weights. All of these things are called weights. So you can set the weights, and you can just set the weights such that and it is just solving inequalities. So that with this configuration, this one can't switch that one off. So it stays on when all three are on. If two are on, then there isn't that much current going. That one can switch that one off. But when there's three, it's like there's too much, so it stays on. Yeah, but that was a good question. Yeah.
Have you found an application of your three-state device yet? Because I think I'm right in saying that, in principle, things like phosphorus transfer would be more efficient if you worked in triplets than it would in pairs. But it's just much harder to implement.
Yeah. So it's very early days, and I think because of my pure mathematics. These limit cycles. See, a lot of engineers won't realize that it's very easy when you look at the nonlinear characteristic of a resistor. It's very easy to make it so the shape is like it's as simple as this. So for one limit cycle, the nonlinear looks like that, and then you get your limit cycle goes kind of like that around there. But it's very easy to set it up. Oh, I'd have to think about this, but it kind of goes bigger and bigger. Non-linearity goes bigger and bigger. And you can kind of have, I can't draw it, but you have one round there, one round there, and they build up. So that's what I did my PhD on. It was how many limit cycles can these systems have? And if you think about it, there's kind of no limit, because you can just get bigger and bigger and bigger. So this again is why we need to speak to the electrical engineering. So I got my PhD. So there's a big table. I remember when I got my results from my PhD, it was funny because you look at it like, so I had this table where you've got the degree of one polynomial and degree of another polynomial, and you want to know how many limit cycles. And somebody had this result. It went up like this. This was the number of limit cycles you can have for the degree of G. And I proved that I was symmetric, so it went up like this. Okay. All right. Yeah. So this is how I got my PhD. And remember, the day I got the results, I went back and I shared a kitchen with all my mates. And I was saying, look what I've done. And I proved it. You get 0, 1, 1, 2, 2, 3, 3. And they couldn't believe they were saying, what? You're going to get a PhD because 0, 1, 1, 2, 2, 3, 3, 4, 4. Yeah, so that was quite funny. But yeah, but that goes on and on. You can have, you can have any number of limit cycles. So not just 3, you could, well, again, there's going to be a physical bound. But there might not be, the engineers might be able to do something that there's no physical bound. You can have any number of states.
Do you hit a physical limit like you do with the transistor?
Probably, I would think that. Yeah, it's probably, yeah. There will be a physical limit, but I don't know what that is. So you can see there's lots of research still to do. And as I say, John and I have been working on this for so long, and we've got all the theory. The theory's been done to death, but we haven't got anything tangible. We need to work with engineers. So yesterday at this meeting, I thought I would go and speak to these eminent professors in working with transistors. I just said, what's the minimum number of transistors you need to build a threshold oscillator? And they didn't know because they don't think in those terms. I'd say 90% of them had never heard of Josephson junctions. And yet in the 1980s, there were Josephson junctions and transistors. And at the time, transistors worked at room temperature. Josephson junction, you have to get down to 4 Kelvin. So the world invested everything in transistors. So all the billions went into transistors. And I think now there's about 5 or 6 companies in the world who work with Josephson junctions. And yet you can see Josephson junctions of the future. Nobody's asked me about quantum computers. Josephson junctions are used in quantum computers. Do you know how cold they have to be? 4 millikelvin. It has to be 1,000 times colder than what we need. 4 millikelvin. And it's interesting, look up, because it's supposed to be the coldest place in the universe. You think, how did it get down to 4 millikelvin? Because nowhere is absolute zero. But how do you get to 4 millikelvin? But that's the kind of temperatures they need in order for quantum computers. And I'm sure you've seen Google and Microsoft have made recent announcements saying they've got quantum computers working, but it could still be 50 or 100 years before we have a proper working, fully working quantum computer. Ours is far closer. If only the world will listen to us, and the Hypers told us we need about $10 million to build a prototype computer, and $10 million is nothing when you consider how many billions they're spending building nuclear power stations. Can you imagine a world where nearly every city's got a nuclear power station? How dangerous would that be? And they don't need it. You don't need it. You can just use the solar panel.
Do you need it all being like a silicon chip?
They can, yeah. So as I say, can, yeah. I'm not sure it's silicon, but they can manufacture. You can manufacture the circuit, and this one. I'm not sure it's silicon, but they can definitely make chip size Josephson junction circuits. The military use these a lot. So they take these chips out in jeeps. When I think they were using them in Afghanistan when you're looking for radio signals. So they're using them, but they're carrying them around in jeeps at 4 Kelvin. There's also a race around the world at the minute to get. So these superconductors obviously work at 4 Kelvin, but we're trying to get room temperature superconductors. And I think the record at the minute, I think they've got up to about 50 Kelvin. Yeah. So around, and if we can build these supercomputers, the supercomputer, it's going to change everything, because you'll be able to forecast the weather in real time. You'll be able to look for new drugs really quick, because normally now it takes a long time to get drugs. This will do it really quickly. The more I think we've just written an article just saying, what if you had a computer 1,000 times faster than this, and it will literally change the world. All the stuff we'll be able to do. They reckon nuclear fusion wouldn't be far away. And the list goes on and on. It literally will change the world.
Further question? So I've got a question or maybe an observation. Seems to me that there are lots of ethical issues associated with improvements in technology to the point where you can do these things in real time. So, for example, FDA approval of medicines generally takes years and years, and it's good at 10 years. You might be able to do this in days, presumably, but there's a risk associated with fast approval for medication which might not necessarily have been appropriately tested. So there's some ethical issues that we'd have to consider. I'm not asking you to answer the question. I'm just putting it out there that there are some ethical issues to think about. However, on the positive side, it seems to me that beyond the sort of environmental benefits that you mentioned earlier, actually there's some sustainable benefits as well. So when you think about the sort of reduction in utilization of water, this is actually quite significant. So using lots of water to cool stations, you can actually use water where they need it. So there's from the UN's perspective, if you look at the UN's 17 Sustainable Development Goals, it would seem to me that you're basically helping to achieve some of those goals. Water preservation, sanitation, for example, that'd be quite useful. Also, you could be socializing the cost of developing computer machines, because I'd imagine if you think of the amount of time that it takes to produce some of these chips, there's a cost associated with that, which you could significantly reduce. And so for developing economies, I can imagine the cost of computers to be far less than what it is today going forward. So there's obviously an economic argument there. The other thing that I'm thinking about is, with your company, are you looking for shareholders? Yeah, I mean, I think maybe at this point now needs to be asking my wife if we can afford to invest in this company here. But I'm thinking actually you're going to make a lot of money.
But
capitalists who understands what you're talking about.
We've got our foot in the door now. Another interesting one is, so there was a guy there yesterday who was talking about automotive, the self-driving cars. So they were talking about chiplets. So the future is chiplets, where you have these chips all performing different tasks in a car and anything. So he was saying it could be 20, 30 years before we have driverless cars. But can you imagine if you had each chiplet was a supercomputer, in a car? And the list just goes on. The more you think about it, you think, wow, it is really going to change everything.
I think we have to stop there, because the more I think about it, there are more complications, more questions that I want to ask, but I think we have time. Did you enjoy the talk?
Yeah.
Very much. Excellent. Thank you very much for turning up. Can we show our appreciation?
London branch, my name is Edward, I'm actually in this department. If you want to join the IMA, if you're not a member, please join. Go to the website ima.org.uk, and I'm sure we'll have a space for everyone.
Right, excellent.
Is the recording finished now?